Very good. I'm going to talk about a joint work with Amit Danieli, who is at Hebrew University and Google. So this is a talk about the power of non-interactive protocols in the local model of differential privacy. And we'll explore that power in the context of learning algorithms in the sort of classical pack learning framework. You can also think about this work as a work about adaptive data analysis. We'll be understanding the power of adaptivity in sort of solving learning problems. So let's start with a brief reminder what a local model of differential privacy is. I imagine most of the people at this workshop don't need this reminder, but just in case you found this video on YouTube and you haven't, I'll give a reminder. So in this model we have say n users, each holding their own data. And these users interact with a server that wants to compute some function on that data. And a protocol in this, and in this general setting, the order of interaction between the server and the users is completely arbitrary and restricted. And the queries of a server might depend on all the sort of values that the server has observed so far. And a protocol in the setting is set to satisfy epsilon local differential privacy if each of the messages sent by each of the users is sent using a local randomizer that has this epsilon differential privacy property. And for every user, the sum of the epsilons used on its messages is upper bounded by this total epsilon budget. And this model is from the paper by Kassevisvanathan, Lee, Nissim, Rashodnikov, and Smith, and we'll be invoking this work quite a few times in this paper, so I'll refer to it as cleaners. I mean, it's often nicknamed. This is a very powerful model. We know how to solve relatively sophisticated problems, hard problems in this model. But it has been observed by many people that in practice protocols that have many rounds of interactions are inefficient and in many cases are basically impractical. And this is due to various kind of network latencies having to synchronize between the users and also general complexity of such protocols. And as a result, sort of the protocols that have been actually deployed in practice are basically non-interactive. And what that means is that the server gets to pick some set of queries, sends those queries essentially in parallel to all the users, obtains the responses, then computes whatever it needs to compute on those responses after observing these queries. So, and it's natural to ask what kind of functions can be computed if you restrict the protocols to be non-interactive, which is exactly a question about what is the power, what are the problems that can be solved. We want to find problems that can be solved interactively but cannot be solved if the protocol is restricted to be non-interactive. So you can, of course, explore this question in the context of many different learning problems. The ones we'll be looking at are so-called the pack learning framework, the classical framework of Valiant. And a problem in this framework is defined by a class of functions that we want to learn, which we'll denote by C. And these functions are just binary Boolean functions over some domain X. And an algorithm is said to be a pack learning algorithm if for every function in that class and for every distribution over this domain X, the algorithm is given ID examples, where an example is a point drawn from this unknown distribution and the value of the unknown function f on that point. Given such examples, the algorithm outputs a hypothesis H, such that with high probability, this hypothesis disagrees with the unknown function with probability at most alpha, where the probability is again taken over this unknown distribution D. So in this basic framework, it's assumed the algorithm needs to work for every function and every distribution. But we'll also look at the version of this model in which the distribution is effectively fixed and known to the algorithm. It's often referred as distribution-specific learning, and this version is referred to as distribution-independent learning. So in our setting, the examples are not given directly to the algorithm. Actually, these are the examples are held by each of the users in the local protocol. So in order to kind of argue and understand what's known about learning with local differential privacy in this model, the main tool that has been used is another model, sort of a restricted model of learning, which is referred to a statistical query model defined by Kearns in '93. And in this model, we have an algorithm which, instead of having access to examples themselves, has access to so-called statistical query oracle for the data distribution, which we'll denote by P. And the data distribution in our case for learning problems will be the distribution over the labeled examples that we observe, which is just the point and its value, where the point is drawn from distribution D over the domain. So in this model, a statistical query algorithm can ask queries to this oracle, and each query is defined by as we usually define statistical query is a function which maps a point in the domain, basically, a data point, which is an example, to some range 0, 1. And to this query, an oracle responds with an arbitrary value v, which is close to the expectation of this function on an element drawn randomly from this unknown data distribution. And the closeness is measured using this parameter tau that is referred to as the tolerance of the query, and roughly corresponds to the number of examples that the algorithm would have in the standard model, where the correspondence is roughly, you should think of tau as being roughly 1 over square root of n. So it roughly corresponds to the sample complexity. So the algorithm can ask additional queries after observing the results and so on and so forth. And the reason why this model is important is that is the fact that also shown by cleaners that that basically this model is essentially equivalent to a local model of differential privacy. Specifically, they show two simulation results, both of which kind of succeed with some probability 1 over beta, and will restrict here and everywhere else epsilon to be at most 1. So they show the first simulation result. They show that any epsilon locally differentially private protocol with m messages can be simulated using O of m statistical queries with tolerance being roughly this beta failure probability over m. And in the other direction, they show that any statistical query algorithm with tolerance tau can be simulated by a protocol. One can simulate this oracle using a locally differentially private protocol, which has n examples where n is roughly the number of queries divided by the tolerance and epsilon squared. And in this case, in this simulation, one obtains the protocol which only uses each of the samples once, so the number of samples is the same as the number of messages. Does it make sense so far? So now, directly from these two simulations, okay, so also one I should have mentioned that an important property of these simulation results is that the protocol that one obtains is non-interactive if and only if the corresponding statistical query algorithm is non-adaptive, which basically means kind of the same thing in this context. A statistical query algorithm is non-adaptive if all of its queries are none of these queries depend on the previous answers, or that all the queries are determined before observing any of the answers from the oracle. So from this result, one kind of directly obtains the following equivalence. A class of concepts C is learnable efficiently in this model, statistical query of statistical queries, if and only if it is learnable efficiently in local model of differential privacy, where by efficiently I mean that it's polynomial in the size of the input and relevant learning parameters. And this equivalence also preserves this adaptivity or interactivity, which again in this context refer to the same thing. So from this result, one can immediately obtain a bunch of nice corollaries for local differential privacy from statistical query algorithms. For example, one can obtain that the class of linear classifiers, or also referred to as half spaces, is learnable efficiently. This is via a result of Donegan and Vimpala. One also obtains that the class of parity functions, it doesn't matter if you don't know what they are, will not be learnable by locally differentially private algorithms, even though it's known to be learnable by central differentially private algorithms, also result from cleaners. And we also know that there are actually very few learning algorithms which are completely non-interactive, but one example of non-interactive algorithm is learning of Boolean conjunctions, which are simple, very simple functions. So now using this tool makes it much easier to separate the models of interactive and non-interactive. And that's exactly what has been done by again, cleaners. They show that there exists a class of functions that is learnable in the statistical query or local differential privacy efficiently or when one restricts the distribution to be uniform over this Boolean hypercube of dimension d. But if you were to try to learn this class non-interactively, you would require an exponential number of sample by an LDP algorithm. So it's a very strong separation. And as far as I know, it's not known for any other. These kind of strong separations are not known for any sort of other problem in any kind of domain, as far as I know. But maybe I'm just missing some literature. So the way they show it, it's a relatively simple construction. They show that the class they pick is so-called masked parity, which basically requires you, once you solve, so in which one part of the domain is masked using a key that can be discovered by solving a learning problem on the other part of the domain, and that sort of forces the algorithm to be interactive. So if you can first find this key, you cannot make any meaningful queries about this learning problem. So again, the separation is very strong, but it is kind of unsatisfying in two respects. The first one is that the class has been designed specifically for this problem. It's not a natural problem at all. And the other the construction inherently only works for distribution-specific learning. If the learning algorithm, if the distribution was not restricted, the distribution could be all concentrated on this masked part of the domain, and which would make it impossible to learn even for the interactive algorithm. So it is natural to ask, in fact has been explicitly asked by cleaners, does this separation hold if one were to look at distribution-independent learning? And of course, it would be even more interesting to separate these things for natural learning problems. So, and this is exactly the problem that we're going to answer in this work. To present the result, I'll need one more concept. Again, let me know if you have any questions. There will be quite a few maybe concepts that are new for some of you. And that is the concept of margin complexity. So let me first briefly remind you what the margin is. So for two sets in Euclidean space of points, one of which is labeled positively and one of which is labeled negatively, we say that they are separable with margin gamma if there exists a separating hyperplane, which separates them, the positive are on one side and the negative are on the other side, and the distance from any point to the separating hyperplane is at least gamma. This is a standard classical notion in learning. And using this notion, the margin complexity of a class of function C, which we'll denote by margin complexity C, is defined as the smallest m, such that there exists an embedding from this domain of the class X to the unit ball in d dimensions, such that under this embedding, each function becomes linearly separable with margin gamma, which is at least 1 over m. And here by function becoming linearly separable is basically means that the positive examples of functions are mapped and the negative examples, these two sets of points, after being embedded into this space, become linearly separable with margin gamma. That makes sense. So this defines a notion of complexity for a class of functions that, again, it's important both in learning, in fact, has been also studied in communication complexity. So with this notion, we can give our sort of main lower bound, which says the following. Let C be any class of Boolean classifiers that is negation closed, meaning that if a function is in the class, then its negation is also in the class. Then any non-interactive locally differentially private algorithm, let's say epsilon 1, that learns this class in the PAC model, distribution independently, with arbitrary error that is less than half and non-trivial success probability, will need the number of examples and messages, which is at least margin complexity of C to the power 2/3. That's the main lower bound. Let me spell out some of the corollaries that make sense. Let me spell out some of the corollaries of this result. The first one for the class of decision lists. You might, for those who haven't seen this class, each function, each decision list is defined by a sequence of decisions. And here the input vector is a d-dimensional Boolean vector. And each decision can check the value of one of the attributes. For example, whether the third attribute is equal to 1. If the condition holds, it will output, the value of the function will be fixed to some arbitrary plus or minus 1. If the condition doesn't hold, it goes to the next decision and could do it for an arbitrary number of decisions. And at the end, everything has to be determined. So for this class of functions, we show, so the corollary of our lower bound is that the number of samples one need to learn it non-adaptively is 2 to the omega, basically 2 to the d to the cube root of d, which is basically exponential in the dimension d. And this follows from a lower bound on the margin complexity of this class due to Berman, Vereshchagin, and Devolve. Another corollary, and the reason why it's kind of separates these classes is that, as shown already by Kearns in '93, if you allow interaction, this class is easy to learn with a number of samples, which is polynomial in D and alpha and epsilon. And the algorithm is very simple. It just peels off these kind of decisions one by one until it learns. It's kind of inherently interactive algorithm. And another corollary one gets from this lower bound is for a somewhat more general class of linear classifiers, and we'll again look at those over the Boolean hypercube. For this class, our lower bound is that the number of samples you'll need is actually exponential in d, 2 to the omega of d. And as I have mentioned, this class, so it follows from a lower bound on margin complexity of these linear classifiers due to Goldman, Hafstad, and Razborov, and Sherstov is the one who kind of noticed that their result implies lower bound on margin complexity. And here, the result that I have mentioned, this class is learnable interactively with the number of samples, which is polynomial in d over alpha epsilon, and this is the result due to Donegan and Van Pala. So that's the result. Let me now, okay, natural question is this, is there a matching upper bound? And we haven't solved this question, but we made some progress. We show also some upper bounds, which are in terms of margin complexity. Specifically, we show that if you fix the distribution D, then and make it known to the algorithm, then for any class C, there exists an algorithm that will learn this class C over this fixed distribution D using a number of samples, which is polynomial in the margin complexity of this class, times whatever the standard learning parameters. And while sort of knowing the D might be kind of a very strong and restrictive condition, we can relax it in two ways. The one option is that if one has access to public unlabeled samples from D, the corollary will still hold. In fact, we can also use kind of this hybrid model in which we have non-interactive access to labeled examples, but interactive LDP access to unlabeled samples from D. And one nice thing about this hybrid model is that actually our lower bound also holds against this hybrid model of, again, non-interactive access to labeled examples and interactive access to unlabeled one. So in that sense, this hybrid model is basically correct. The learnability in this model is characterized by the margin complexity. So now, okay, that's basically the result. Let me know if you have any questions so far.
Let's see if I understand. So this learner knows D, say,
or alternatively, it has access to public unlabeled samples from D, or alternatively, instead of knowing D, it can have interactive access to some users who only hold the unlabeled samples from the distribution. They don't know anything about the label.
I see. But you're not sure if this upper bound holds in like fully distribution independent setting.
Yeah. So it's a fully distribution independent, but there is some kind of special access to the distribution D. You need to know something about it. Instead of knowing it, you can replace it with some access to samples.
But you're not sure if this is necessary.
I don't know if that's necessary. I suspect that it is. Anyway, let me now briefly. Yeah.
The idea is that you know it and you can sample from it, or
yes. The only thing you need is to be able to sample, and even less than just sample. We'll see. Actually, we might have time to see the upper bound. Okay. So let me briefly describe you actually how do we prove both of the results. So first of all, the lower bound, and just to remind you, basically using the characterization by statistical queries and kind of the contrapositive of the main lower bound can be stated as follows: if C is a negation closed set of classifiers, then if exists a non-adaptive SQ algorithm that uses Q queries of each of tolerance 1 over Q, then and learns the class with some non-trivial error, then the margin complexity of the class that has been learned is at most O of Q to the 3 seconds. It's just, again, the contrapositive of the result of the lower bound, stated in the statistical query framework. To prove this result, sort of the main tool is this kind of correlation, the notion of correlation dimension of a class of function C from an earlier work by myself. And the correlation dimension of a class C is defined as the smallest number t, for which there exists t functions, each of which is mapping the domain elements to this -1, 1, such that for every single function in the class C and every distribution D, there exists one of those functions that has non-trivial correlation with the unknown function. So we want to kind of cover the set of all functions and all distributions with some set of functions that are correlated, some small set of functions which correlated with each of those. And the reason why we need this dimension is that it has a simple relationship to the margin complexity, has been shown by myself and then sharpened by Calvé and Simon, that the margin complexity of a class C is upper bounded by correlation statistical query dimension to the power of 3 halves. And so now with this notion, in order to prove our lower bound, all we need to show that if there exists a non-adaptive statistical query algorithm that uses Q queries of tolerance 1 over Q, then this correlation statistical query dimension is at most Q. And the proof is pretty simple. Again, we'll do it for deterministic algorithms, which makes it even simpler. In general, somewhat different. The path for randomized algorithm is slightly more complicated, but not conceptually so. So let's assume that we have a non-adaptive statistical query algorithm, which uses Q queries. And because these are non-adaptive, we can assume that they're just fixed in advance. There's a fixed set of queries. Now, given these queries, we can decompose each query into two parts. One is, this is kind of a simple identity that one can check by just plugging two values of the label y. So each query can be decomposed in these two parts, and we'll refer to the first part as G. It kind of does not depend on the label. And the second part, which is just a product of the label with this function. So we'll get two functions out of each query. And this decomposition gives us, implies that the expectation of each query that the oracle estimates is just the sum of expectation of this this function, which does not, again, depend on the target function, plus the correlation of the second part with the target function, just two parts to the query. Now, if we assume that now we claim that this set of HIs, this part of the function for each of the queries, will be the certificate for this cover for this correlation dimension. And to prove this, we assume that if this doesn't hold, then we'll arrive at the contradiction in the following way. So if this correlation is at most 1 over Q, then basically the answer to the query with function f will be the same, essentially the same as the answer to the query for the negation of the same function, because again, this correlation part is close to 0, and then we only left with part which does not depend on the label. And now if this holds for all the queries, this basically means that the queries cannot distinguish, there exists some function for which the queries cannot distinguish between the function and its negation. And if you cannot distinguish between the function and its negation, you cannot learn with any non-trivial accuracy. So that's the end of the lower bound. And since I don't have much time, let me go and say something briefly about the upper bound. Hope it makes some sense. So the upper bound is, just to remind you, we want to give an algorithm which learns in time polynomial and margin complexity. And to remind you, the margin complexity is sort of the smallest m under which there exists embedding in some d-dimensional space where the functions become linearly separable. One sort of annoying issue is that the notion of margin complexity does not say anything about what this dimension is. It potentially could be exponentially small, so it doesn't immediately lead to the algorithm. But there is a sort of a standard fact about margin complexity is that you can always reduce this dimension to be much smaller. Specifically, you can use a random projection and then get an embedding into a space of roughly whose dimension is roughly margin complexity squared, and you'll lose only a constant factor of the margin. So you can reduce the dimension to be roughly polynomial in margin complexity. Now, having reduced the dimension, all we need is to be able to learn large margin classifiers in relatively small dimension. And the way to do it, there's one way in our paper. I think you can do it even simpler. Let me see if I can convince you. So we'll look at the sort of the standard perceptron algorithm. I imagine most of you, some of you at least, have seen it. And what this algorithm does is start with sort of all zeros vector, and then takes any examples. If the example, it maintains some weight vector which describes a linear classifier. If the current half space does not predict labeled correctly, then it updates the weight vector by adding to it the sort of this point multiplied by its labeled, and then repeats this process until convergence. So in our setting, of course, we don't have the examples themselves. It has been observed that you don't, in this distributional setting, instead of using examples themselves, you can use expected updates, which is just the expectation of this update vector, y times x, condition on this example being a counter example. So you need to compute this expectation here is a vector. And to compute, you can see here that if you were to try to compute this expectation, it kind of depends on the current, the condition depends on the current value of the vector, so it is kind of an adaptive algorithm. But if you look a little more carefully, this conditional expectation is just, by the definition of conditional expectation, is just the expectation of the product of this vector times the indicator of the condition divided by the probability of condition holding. This probability of condition holding is just some scalar and actually not too small. And all the updates will go through if you just don't quite, if they have some additional factor. So all we need to make sure is that we can estimate this expectation. Now, this expectation, again, if you look at it a little more careful, is just the expectation of x times the 1 minus the sign of the sort of the value of the current current classifier, which is just again just decomposes into the expectation of the product of this xy plus x times the sign of this condition. And from here one can see that this part is non-adaptive. It's just that basically this vector is just a vector of correlation of each of the attributes with the label. And this part does not depend on the label at all. It is it's another expectation, but it is adaptive. It depends on the current value of the current hypothesis, but does not depend on the label. So if you know the distribution, you can just compute these expectations easily. So the only thing I didn't tell you is how do we estimate these expectations of vectors in the LDP model or statistical query model, but it's a problem that has been solved. You can do it naively, or if you want to do it a little more in a more sophisticated way, you can use the algorithm. In LDP, you can use the algorithm by Ducci and others. And if you want to do it with statistical queries, there is a paper by myself, Cristobal Guzman, and Santosh Vimpala. So that's all that I wanted to say about the upper bound. Let me go to conclusions. So first of all, just as a brief summary, we show the new approach to lower bounds for non-interactive LDP protocols, which reduces, so the approach reduces them to a margin complexity lower bound. And to be fair, most of the heavy lifting is done by these margin complexity lower bounds. None of the results we're relying on is kind of simple. They're actually pretty sophisticated results. But once you get this, but because this notion is kind of a classical notion that has been studied, especially in communication complexity, we do get some lower bounds for classical learning problems. And another nice property of doing this, all these results via statistical query model is that we get essentially the same result for another well-studied model, which is so-called communication constraint protocols, where again it's a distributed protocol, but each user can send only a small number of bits in each round of interaction about their data point. Again, this model is also equivalent to statistical queries, and you get the same set of results for this model. So another implication is that one can say that interaction is necessary for learning. We again, in the context of adaptive data analysis, we consider all these protocols that ask statistical queries adaptively. But we don't have much evidence. We don't know whether this is actually necessary. So this is one way to see that this interaction or adaptivity is necessary for achieving some, for learning in particular. And let me mention a couple of open problems. And basically this entire area is a big open problem. So it's kind of much easier to state, and pretty much any question, no matter how basic, is probably open. Let me mention just a couple of those which are related to this work. First of all, we don't get, it would be great to have a distribution-independent learning, which is polynomial in margin complexity, or prove a lower bound, which is probably more likely. The other thing, which is kind of a significant limitation of our lower bounds, is that they only hold against completely non-interactive protocols. I don't know whether they hold even for protocols which use 2 rounds of interaction. And finally, sort of, these, as I mentioned, these pack learning problems are potentially not the most interesting in the sort of for modern practice of machine learning. It would be much more interesting to understand what happens in stochastic convex optimization, and there we still don't have any lower bounds for the LDP, but there is some progress that Abradeep, I think, is going to talk about later today. That's it. Thank you.
Question? Anyone?
Could you try to describe how we can bring these things to application domain? I mean, how, in terms of implementation, these things.
So I mean,
the results are mostly theoretical.
So lower bounds basically mean that you cannot do that. Like at least if you're trying to do if you want to implement a non-interactive local protocol, that's sort of the main could say the main result is there are things that you cannot do. So you maybe, again, unless you make some additional assumptions and things like this. We also have an upper bound, which is a learning algorithm, again, depending on whether the assumptions fit your problem. I mean, implementing it is kind of easy because it is a non-interactive protocol. The specific algorithm that we give basically only needs to compute the correlations between the label and each of their attributes, something that we already have existing protocols that do this in practice. So basically that's pretty easy to implement and can be done.
Great, let's thank, I guess, Vitaly again. You have until 1:45.